So for the Long River survey itself, unfortunately, the increase in target list, species list is making this item inconsistent at all. The next, temporal scale of the survey. So here it's a figure demonstrating the sampling time period for each single year. So marked with the starting date in green and end date in red. So it's easy to tell that, during the late 80s and early 90s, there had been a shortened survey period for these years, and after which it has remained relatively stable, but with a few years really stand out in terms of the survey ended dates. So this is at an annual scale. So if we further zoom into every day by looking at the sampling events during day and night, we also notice there has been a block of time where we only have night sampling event, while in other time period we may have a proportion of sampling during day and night, but are not balanced for each year. So we may have only night sampling at the later end of the year, and during the early of the year we only have day sampling. So that could be also an issue. So temporally the survey was also not consistent. In terms of the sampling spatial area, so here is a violin plot showing the, sorry about this small y-axis labels. It's river kilometers here. So it's a river kilometer sampling range for each single year, with the bandwidth of the violin representing the relative sampling effort of that river kilometer. So we see that for the first few years, the lower river region, basically Battery Park region, was not sampled at all. Even after that, we can see that the sampling effort were heavily concentrated in the lower river region. So that is also another issue for the spatial consistency. And in terms of the sampling depth, also demonstrated through this violin plot, we see the sampling depth have been also heavily concentrated in the shallow water, which is below 40 meters in most recent years, and most of the samples occurred below 20 meters in depth. Sorry about the caption here, it's mislabeled. So anyway, for depth sampling, we also did not have this kind of consistency. Last but not least, sampling gears. So we compared the sampling events using two gears in terms of the depth. We see that for epiphytic slab and Turkachos, we see a very substantial difference in terms of the sampling depth, measured with median value or maximum value. So which means that even for the same species of same life stage, when we use two different gears, we can end up with totally different catchability for this species. So this also renders the last item inconsistent. So going back to this checklist, 5 out of 7 items here are not consistent for the Long River survey data. So what does it really mean for our for how we use this data to calculate the abundance? So assuming we have a perfectly consistent fisheries survey, when we try to estimate fish abundance, it should be a simple function, not simple, a sole function of ecological factors plus an error or uncertain term. So we can attribute all fish abundance estimates to maybe population dynamics or other environmental factors. But with this Long River survey, which has inconsistent sampling protocol, the fish abundance estimate could be subject not only to ecological factors and uncertainty, but also a sampling effect, a variability due to sampling effects. So in this case, we could end up with such a situation. So here, assuming we have 2 results estimated with the Long River survey uncalibrated data. So first one, we estimate average of 20 fish at 10 meter depth during night in spring. And the second result, we estimate average of 10 fish and 20 meter depth during morning in fall. So can we simply attribute the difference between these two results to solely ecological factors? No, absolutely not, because we have a variability due to the due to the sampling effects in this survey. So this leads to our task, which means we need to remove that variability term in this kind of survey. And this process, we can call it a calibration. Sometimes you can call that standardization based on how you want to use the data and what is the purpose of the data cleaning. All right. Okay, next we're gonna be delving a little bit into the technical procedure we developed for data calibration here. So, since calibration is all about modeling and understanding the variability term here, so we have to identify suitable model structure and the variables to include. So we start by preparing the data by compiling and standardizing the historical data set, reviewing SOP and NYCAFS report to understand what has been really changing for the protocol, which have been already covered in the previous section. Then we did some data mining to really quantify and factorize or identify some of the key explanatory variables affecting sample effects. So we did this for each species and life stages separately. So we did not include species or life stage as a variable in the model. So temporarily we included sampling year, sampling day of year, sampling hour, and spatially we have a river kilometer. And other than that, we also have sampling depth and sampling gear. Okay, so with these variables identified, we then go forward to develop statistical models, and I'll be elaborating on this in the next few pages. So with model developed, we try to select the best fit model. So this involves which structure we want to use and to choose a model based on their goodness of fitting indicators, including AIC, variation, and deviance explained. So once we have the best fitting model, we still want the model to have adequate predicting performance. So we did some model validation, basically comparing the observation value with the model prediction results in terms of their performance under different sample size with k-fold analysis and their performance under different lengths of time series data with retrospective analysis. So once we got the best fit model with adequate predicting performance, we can use this model to generate model calibrated data. So if we only extract the year effect from the model, then we end up with a temporal trend in fish abundance by year. So we can call that a model-based abundance indices. It's a concept opposite to the design-based indices, which we will compare in the results. Okay, so because we don't have so much time to cover all the details here, but if you are interested, feel free to refer to this paper. Okay, so to calibrate this, to develop this procedure, we choose several case study species and representative life stages here. So to make sure the analysis is simple enough and do not contain unnecessary complexities, we downsize the data set for each species by presuming their spawning season and the spatial distribution range. And in terms of the species selected, we tend to cover different status of species in the survey design, which means we have species strap S, which is always the target species since the start, and we have 3 newly added species to target species after the survey launched for a few years. We have white perch, Atlantic tomcod, and American shad. We also have American eel, which is not a target species throughout the entire survey period. Just wanted to include some considerations of survey design factors. Okay, so in terms of the model structure, so above is a simplified general model structure. So we try to develop functions based on all these variables here. And we use CPUE to represent fish abundance. So here is a list of candidate models we have explored, and we also explored a few machine learning models that unfortunately did not converge at all.